All right, so we're gonna talk about now the average rate of change. So I briefly mentioned this, they kind of described it at the beginning of this section, is as we get further along, first, our rate of change, our slope, is very big. But as we go further along, the rate of change gets smaller and smaller and smaller. So it's still growing. It's just growing not as fast as before. So what we're going to do now is talk about that. So if I do the slope from -1 to -2, I have a rate of change of 2. And if I go from -2 to -1 on my x, we're talking about our x's, the rate of change is 0.282. So it's smaller. And as I keep going along, my slope keeps getting smaller and smaller and smaller. So what's happening here is I'm doing, first I'm going like this, then I'm going like this, and like this, and that slope just keeps getting to the point where you can't even see it as I'm writing it down. So let me use different colors here. So we have this S. And as I do my rate of change, first it's like, oh, that's not that big. It's a little bit bigger, 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 less big, less big. So as I keep going to the right, I keep getting a smaller rate of change. And you can see that here. It's like, oh, wow, this one's only a fraction. Whereas where I was with the negatives, it was a big rate of change. So slope keeps getting smaller and smaller. It's still growing. It's just, it grows less and less each time. You can see that here with the cubic root, as I'm going negative, that, then it gets smaller. As I go from negative to positive, that's a big rate of change from 0 to 1. And then as I go from 1 to 2, it's the same rate of change, but as I go from 2 all the way to 3, it went down. Our rate of change went down. So basically it's saying here if we're going from 0, to 1 on our x value, the rate of change is going to be the same. But as I get further and further along, you see that as I go from positive to negative, it's going to create this smaller rate of change. So as we branch out from 0 onward, it gets smaller, and smaller as we go out. And if we go from 0 downwards, it's also going to get smaller. So as we're going from 0 to positive, 0 to negative, it gets smaller, and as we go from 0 to positive, it gets smaller too. So that's what it means by the rate of change. It's always growing, but it just grows less and less over time. So this is going to grow. It grows a lot from 69 to here, and then it grows less. It starts growing a little less and less. It's still growing. It can go all the way to infinity in theory, but it's growing less. So I think this one they're talking about a balloon. So what are they talking about here? Oh, the radius of the balloon. So as the balloon gets bigger, the radius at first, it's like, oh, the radius is going to grow huge. And as the volume of the balloon gets bigger, it's less of a change on the radius. Yes, the volume gets bigger, so the radius is still going to get bigger, but not as much. And the reason for that is, think about it. If we go from here to here, that's a big change in the volume and the radius. But as we go from here to here, the volume is bigger, but it takes less of a change in the radius to have that volume, because look at all this volume right here, all of this, that's a lot. You still need less of a change in the radius. So even though the volume's increasing, it's not as much as before. All right, and again, they're still calculating that rate. So this is still talking about different rates of change. In this one, they were talking about P. What's our P? Because I know we're talking about the volume. In this case, we're talking about speakers, the volume and the watts. Oh, voltage. There we go. Voltage and power. Okay, so the voltage is going to increase, but it's going to have less of effect on the power. So that's what's happening here. Even though we're increasing power, the voltage doesn't increase as much over time. So here's our power. It starts affecting the voltage less and less the more power we go. All right, so let's do an interpreting key features of rational functions activity. So let's do our lesson activity. All right, so identify the key features of this graph. All right, so key features here, we're going to talk about determine that the function is are decreasing. So this function is, we can just copy this word because monotonically means it's only is monotonically increasing. That means only increasing. State the end behavior as the x gets bigger, the y also gets bigger. There's no end behavior to the left. So going as x gets closer to 0, because that's the only thing we can do as it gets closer to 0. It never gets past 0. So we're going to say as x gets closer to 0, y gets closer to 0 until eventually, if we get there. Find the x and y intercepts without using a calculator. The only x and y intercept is the origin. So this is just saying that our x and y intercept is 0, 0. So the only x-intercept is the origin. State the domain and range. We kind of already did that. The domain is 0 to infinity, so 0 to infinity. The range is 0 to infinity as well. One thing I normally recommend is saying using the infinity symbol, but for some reason the equation editor doesn't have infinity symbol. Interpret the key features you noted in part A in the context of the problem. So in this case, they're like, let's talk about the actual question itself, which I hardly ever read. So it's a good thing that they reminded me, like, hey, don't just answer the question, like figure out what we're talking about here. Like, okay. So science class is performing, they're dropping height. So this is the seconds and this is the height starting from the ground. Okay, so how long it takes, okay, to science class is performing an experience that involves dropping objects from various heights. Starting to it takes to hit the ground upwards of 8 feet. The function is this, where x represents the distance from the ground and t take time it takes Susan to drop it to hit the ground. So basically, the further we go, the longer it should take to hit the ground. So it growing monotonically means the further it is from the ground, the longer it takes to hit the ground. Pretty obvious there. the domain means we aren't doing it from below the ground, which is pretty obvious, below the ground. The range means we aren't using negative time because that's impossible. Kind of saying it to both, but more talking about that negative time thing. We don't rewind time, but it can be interpreted both ways. And that's pretty much it. We can talk about it going to infinity, but we're really not going to do that because we're not talking about that much. All right, so now we're going to do another problem. Just kind of seeing how much this is going to involve. All right, so suppose the market research department of a famous bakery has determined an aesthetically aesthetically pleasing donut has a thickness that is twice its inner circle of the radius. The radius of the donut hole. The formula for the inner radius of the donut is given here. So this is the radius of the donut, talking about the volume. So basically what they're saying here is there's a specific way to make this donut, all of this volume, be involved with this radius right here, the inside radius. Mainly because maybe they're thinking, so they're saying that it looks better. So let's say something is not, so they're basically saying you don't want a tiny radius for a giant donut. You also don't want a donut where, oops, why isn't this deleting? You also don't want a radius where the donut has a huge radius and a tiny volume. So they figured out this formula basically. All right, so here's a chart. Identify some key features in the chart that describe the end behavior of the donut. So we're going to say here, well, first of all, we can't have a negative radius. That's kind of weird. But I think they're doing it to just be symmetrical. So one thing that we'll notice here is looking at this, if we're at negative 30, the volume is negative. So it looks symmetrical on the negative and the positive by taking the absolute value. So values of x and y. So if we take the values of x and y, we find that it's symmetrical. It's the same thing. Find the pivot point. The pivot point is 0, 0. So obviously if it doesn't exist, that's our pivot point. Without describe the end behaviors. So that's one thing I didn't mention, the end behaviors. As x gets bigger, so does y. As x gets more negative, y gets more negative also. So this one, it does have an end behavior for the left side. And that's because it's a cubic function. So that's making this s. The other one didn't have an end behavior for the left because it's had this intersection there. The pivot point is obviously right here at 0, 0. All right, so let's talk about this. Interpret the key features and context of the problem. So, so key features in terms of the problem, since a negative radius is just on the other side of where we measure, it shouldn't affect the volume. This is why if we take the absolute value, it is the same. The pivot point happens because if we don't have a radius, there is no volume. So that pretty much describes most of it, right? If we're talking about a negative radius, so if this is our radius, a negative radius would be this way. The only reason why the volume is negative instead of positive is because it's math. So that's why we have to take the absolute value. So that's what I'm talking about there. Again, if this doesn't make any sense, guys, like read it to yourselves. If it doesn't make any sense, use your own words. All right? Use your own words, use your own critical analysis to be able to finish this. All right. So a car company is testing how well its car handles. So we have this formula here. Now they want the average rate of change. So how we're going to calculate this is we're going to go into our equation editor. What I recommend is you can actually make this smaller. That way we can actually look at what we're doing here. So we're going to do, it's always new minus old. So if we look at this new one here, we have this, well, because of how a chart is, we can't really put it here. We're going to have to put it right here. So let's do that. We're going to do new over old. So we're going to do 33.54 minus 32.52 over 50, this 50 right here, minus 47. What I recommend doing is plugging all of this into Desmos. So we're going to do equals. Let's see what Desmos has to say about this. So what I recommend doing here is starting off with a division sign. That way we have our fraction. Be careful because when you change the tab, Desmos is going to start writing over here. So I'm just going to copy this. Hopefully this isn't too complicated because Edmentum is kind of dumb. So let me do this. Yep, Edmentum's dumb. So I don't know why they don't just use a normal text editor. It's just baffled me. 33.554. And our other one is 32.52. So 32.52. We're going to make this over 50 minus 47. And we get 0.34. So 0.34. Okay. We're going to use the exact same thing. So if you're lazy like I am, I'm going to copy this, Control C, Control V, but we have different numbers now. So what we're going to do is we're going to highlight it, go to Equation Editor, make this smaller so we can make the appropriate changes. Our old is the same as our old new. So what I'm going to do here is I'm just going to delete this part. And I'm going to put 35.50 minus, and I'm going to delete this part. The new became old, and then I'm going to put 56 minus that 50. All right, I'm going to change this part, and I need to make those same changes to my Desmos. So I'm going to go over here, and I'm going to do the exact same changes. This was 35.50 over, we're going to get, 30.450, forgot to put that minus sign. Change this bottom, and this is 56. So I get this 0.327. 0.32, you can say 67 if you want to give it a little more decimal places. All right, and we're going to do that for every single one of these. So I'm not going to do that along with you in the interest of keeping this video more concise, but we should start noticing is that it gets smaller. This does have more digits, but 0.32 is smaller than 0.34. So you might have to do some more digits to see those changes. But that's all we're doing. We're just changing this. It's always going to be the new. So that you can see that right there, this new minus the old. So this is going to go there, divided by the new x minus the old y. So that's just a fancy way of doing this formula, the y2 minus y1 over x2 minus x1. In other words, new y minus old y over new x minus old x. That's what these little subscripts mean, too, the newer of the two. For your self-evaluation, honestly, if you're having trouble understanding what they're saying, just say, I didn't understand the question. I answered it to the best of my abilities. But some of it's a little weird. Like, what does end behavior mean? Describe what you don't understand. So be like, I don't understand what monotonically increasing is. And by the way, that just means always increasing or always decreasing because it's monotonic increasing or decreasing. State end behavior. Be like, I don't really know what an end behavior is. Like, describe what it is you don't understand. Take that into account when you're asking this. This isn't about, oh, my answer looked like the correct answer I submitted. That's really easy to do. This is about how you feel about the answers. So moving on. Now we're going to talk about graphing these functions. All right. So let's see. Let me take a look because I'm thinking this is going to have to be another part. All right. So this does look pretty self-explanatory. Yeah, okay, cool. We can definitely talk about this. I was trying to see if we had enough time. So features that we're gonna understand, obviously, one thing that we notice is a cube root, when it's a fraction, grows faster. But as soon as we pass that threshold of the 1, it grows slower. So after 1, a higher power or a higher root grows slower than a lower root. But before 1, so when we're still dealing with fractions, the higher root grows faster. And that's because it's easier to get those decimals with smaller numbers. Like, let's think, for example, 0.8. If I take the cubic root of 0.8, it's 0.2. If I take the square root of 0.9, it's going to be, well, it's not even 0.3. It's a bigger number because of how decimals work. It's not 0.2 because 0.2 cubed is 0.008. So you do have to deal with bigger numbers when you're dealing with fractions. So that's what I mean by it grows faster. That was just a bad example when I made a mistake when I was talking about that. It's just in order to get this 0.8, it takes a lot more work than just 2 times 2 times 2. Because if I do 0.2, it gets me this 0.008. So the numbers are a lot different when we're cubing fractions. Fractions work a lot differently when we're multiplying. It's going to be like 0.99 something. So let's say if I did this, there's not even a cubic function here. So what we would do is like 0.8. If I wanted to find the cube root, I would raise this to the, oh my gosh, 0.8. I would raise this to the 1/3 power. That's the same way you do roots, the 1/3 power. So I get this 0.3333333 power, and you see it's like 0.9 something. So even though it's a 0.8, you have to do 0.9. It's a bigger number. So that's why the rate of change is so much when we're going from a small decimal to a bigger decimal. But once we get to 0, the rate of change is different. Main changes that we're going to talk here, if it's outside the root, if we're adding something outside the root, we're adding something to the y. If we're subtracting something from the x inside the root, it makes it go backwards. It's the opposite behavior. Subtracting from the x is going to have an opposite behavior on our y. The reason I like to think about this is if we plug in a 2 for the x, this 2 is behaving like a 0 because we're taking the square root of 2 minus 2, so we're taking the square root of 0. So that's why if we're subtracting from the 2, it's really moving the graph to the right. A lot of people think it's backwards. What else can we talk about? Or what else are we talking about here? Again, it's mainly this thing of what's happening as we're doing this. So we just plug in an x and we see what the y is. So they're missing a column of where we're doing all the work, or several columns, I should say. So we see this. So -3, we went down 3. We added 1. So normally a graph would look like this, but we went down 3, so we're down here. I should probably do that in another color. So we're down here. That's that -3 here. And then we also, after that, we're going to add this 1. So that's what made us go this way. They're just doing it in little dots. If I plug in a -1, what I get, plug in 2. We can see that from our graph over here. If we plug in a -1, that these are the little dots that make it. Then we connect all those dots as best we can on that curve. So if I'm doing this graph here, I'm trying to get this inside value to be 0. Why am I trying to find this inside value to be 0? Well, as we know, that's the smallest square root we can do. We can't do negatives. So if that's the smallest square root we can do, we want to find that so we know where our starting point is. From there, we can graph the same. So in order to find our starting point, we have to make inside the square root 0. So that's what we did here. That's our inside point. If we do other numbers, so cubic. Well, cubic is our pivot point. So now if we do this, sorry, if we go 9 above, it's a 2, and if we go 9 below, it's a -4. Seems weird, but you'll see what happens here. The growth rate are the same. Down and over, up and over. They're just negative. And then if we draw the curves, we can see those curve changes. So I'm going to cut the video a little short. Hopefully this doesn't mean it's going to be a very tiny video tomorrow. Um, but as always, guys, I do highly recommend watching this. So this also gives you a good break to stop watching this, go into your tutorial, and watch this before you watch the next video. So if you have this on autoplay on YouTube, I recommend just closing the tab and going to your Edmentum and watching this video. I will see you in the next video. Hopefully, like I said, it's not going to be way too short.